Dear students, today we are going to discuss about chapter number 9, gravitation. Gravitation. In gravitation, we are going to discuss about Kepler Laws, universal law of gravitation, and acceleration due to gravity of the earth, and acceleration due to gravity above and below the earth's surface. And also we will discuss about gravitational potential energy, escape speed, earth satellites, and geostationary and polar satellites. I hope you have learned some topics about gravitation in your previous classes. The first one is nothing but uh, geocentric geocentric theory. Geocentric theory is proposed by Ptolemy, and it is nothing but geocentric theory is nothing but all the celestial objects revolve around the earth in circular orbits. Here, celestial objects are nothing but planets, stars, including sun. Here, the center is nothing but revolve around the earth in circular orbits. Geocentric. Geo is nothing but earth. As earth is the center, remaining all other planets, stars and sun revolve around the earth in circular orbits. This is the geocentric theory proposed by the scientist Ptolemy. And another theory is later the scientist Nicholas Copernicus. He has given heliocentric theory. Heliocentric theory is nothing but in which as per this theory, all planets and stars revolve around the sun in circular orbits. Here what is there at the center? Sun is there at the center. So this theory is being proposed by Nicholas Copernicus. Later, another scientist, Tycho Brahe, he also taken a very large number of observations and took the readings with his naked eye. He took observations of the motion of planets with his naked eye. Later, his follower, his student, called Johannes Kepler, analyzed the data taken by the Tycho Brahe and concluded that heliocentric theory is correct. And drawn three laws that we are going to discuss about the Kepler laws here. Kepler's laws of planetary motion. Now we are going to discuss about Kepler's laws of planetary motion. We are going to discuss about Kepler laws of planetary motion. Okay. So here the first law is nothing but law of orbits. First law is law of orbits. It states that all the planets revolve around the sun, revolve around the sun in elliptical orbits, with the sun being at any one of the foci. Here foci means it's a point. See here, I am taking a ellipse here. See, law of orbits tells us that all the planets revolve around the sun in elliptical orbits with the sun being at any one of the foci. See here, I am drawing a ellipse. Okay, so this is called as the semi-major axis, and this is nothing but semi-minor. Sorry, this is major axis, and this is nothing but minor axis. So this is nothing but center of the ellipse. And see here, ellipse has two focus. Ellipse has two focus, that is one focus, another focus. These focuses are equidistant. These foci are equidistant from the center of the ellipse. Let this foci is F1 and this foci is F2. This focus is F2. See here, the distance from here to here is nothing but E into A. Where E is nothing but eccentricity. It tells us it is the property of the shape of the ellipse, eccentricity. If eccentricity E is equal to 0, that means E into A is equal to 0. That means both foci merge together at a center. That means EA distance is equal to 0 for this focus, and for this focus also E into A equal to 0, so that this will come to center, this also will come to center. So the shape which has only one center point is called as the circle. If E equal to 0, the shape is nothing but a circle. Okay, for if E is equal to 1, that means if E is equal to 1, E into A is equal to simply 1 into A, that is nothing but A. In that case, this focus comes to this point and this focus comes to this point. Okay, in that case E into A is equal to simply A. So in that case the shape will be like this. This type of shape we call it as a parabola. When E is equal to 1, we call it as a parabolic shape. Parabola. E equal to 1 indicates parabola. For ellipse, E is in between 0 and 1. E is nothing but eccentricity in between 0 and 1 in the case of ellipse. For the case of circle, eccentricity is equal to 0. And in the case of a parabolic shape, the eccentricity value is equal to 1. Okay, so this E, eccentricity, talks about the shape of the ellipse, shape of the orbits. Okay, see here, um, all the planets revolve around the sun in elliptical orbits with sun being at any one of the focus. Let us consider the sun is at this location. Here is the sun. Here is the sun, and all the planets revolve around the sun in elliptical orbits with the sun at one focus. See, this is the shortest point from the sun. Nearest point is called perihelion, uh, perihelion or perigee, and farthest point from the sun is called as aphelion. We call it as aphelion. Farthest point from the sun is called as the aphelion, and closest point from the sun is called as the perihelion. See here, all the planets. Let us consider this as the planet, and this is nothing but sun. All the planets revolve around the sun in elliptical orbits like this. Here, let us consider this point is nothing but O, and this point is nothing but perihelion point P, and this is nothing but A. Here, OP is equal to OA. OP is equal to OA. OP is equal to OA is called semi-major axis. Semi-major axis. OA is called semi-major axis, and OP is also called semi-major axis. Now we are going to discuss about Kepler's second law of motion. Here, Kepler's second law of motion tells us about laws of areas. See, we are going to discuss about laws of areas here. In the case of laws of areas, I am taking elliptical orbit like this, and this is nothing but major axis. The distance from center of the ellipse to this one is nothing but semi-major axis. Semi-major axis, and whose length is equal to A. See here, as per the first law, the sun will be at any one of the focus here. This is the sun, and I am taking a planet. This is a planet. The line that joins sun to planet is nothing but this is the line. Okay, the laws of areas tells us that the line which joins planet and sun sweeps out equal areas in equal intervals of time. This is the laws of areas. Kepler's second law of motion. The line which joins planet and sun sweeps out equal areas in equal intervals of time. So here the distance from sun to planet, let it be r, and the direction of velocity, we know always the direction of velocity is along the tangential direction. Okay, in a time interval of delta t, let the planet moves from P to P dash, point P2. Let the planet is initially at P, and it moved up to a point of P dash at a time interval of delta t. Okay, at a time you will be finding a planet at this position. Okay, let us consider this area is nothing but A. This area is A. So here area is nothing but area of the triangle is given by area of the triangle is equal to half into length into height of times length into height. Here half times length is nothing but length from sun to planet is r, and in a delta t time interval distance traveled, in delta t time interval distance traveled is nothing but velocity into time. Distance traveled equal to velocity into time interval. So here length is r and height is nothing but v delta t. So v delta t. V delta t is nothing but v delta t is distance travel by planet in delta t time interval. In delta t time interval. Therefore, here the area delta A is equal to half into R into V delta T. So, when I bring this delta T to left side, it will become delta A by delta T is equal to half into R cross V. I am multiplying both sides with, I am multiplying and dividing with mass m here. Multiplying and dividing with the mass m. So here half is half, half is half. Here I am writing r and m 1 by 2m. 1 is already gone, 2m is already written, and r is written already. R cross m into v is nothing but m into v. So mass times velocity is nothing but momentum. Therefore delta A by delta T is equal to 1 by 2m into r cross p. R cross p is nothing but 1 by 2m into r cross p is nothing but angular momentum L. Okay. For any central forces, angular momentum is constant. For any central forces, angular momentum is constant. We have discussed this in 7th chapter. Angular momentum is constant. So L is constant here, and 2 is constant, mass is also constant. So everything is constant. Therefore, delta A by delta T is constant. That means delta A by delta T is nothing but area sweeps out by the planet, by the line that joins planet to sun sweeps out equal areas in equal intervals of time. Delta A by delta T is constant always. That means the line which joins planet and sun sweeps out equal areas in equal intervals of time as delta A by delta T is constant. So that means, see here, when at later time, if you find the planet at this location, after same time interval delta T, let us consider this planet moves from here to here. In this case, the area is nothing but this one. So as per the statement, this is nothing but A1 and this is nothing but A2. So as per the statement, if delta T is same in both the cases, then A1 is equal to A2. That means sweeps out equal areas in equal intervals of time. This is all about laws of areas. So this is second law of Kepler's planetary motion. That is, the line which joins planet and sun sweeps out equal areas in equal intervals of time. We proved this already. Next I am going to state Kepler's third law of motion, planetary motion. Now Kepler's third law of planetary motion is nothing but, it is also called as law of periods. Law of periods. the square of the time period. Time period is nothing but time taken by the particle to move one complete revolution. We have discussed already. The square of the time period, the square of the time period of revolution of a revolution of a planet is proportional to the cube of semi-major axis. Cube of the semi-major axis. That is, in mathematical form, square of the time period is proportional to cube of semi-major axis. Here, semi-major axis is nothing but I have given you already. Semi-major axis length is equal to A. Therefore, T square is proportional to A cube. This is mathematical form of Kepler's third law of motion, that is law of periods. And see here, law of periods is the law of areas. Second law is nothing but law of areas. Law of areas is the consequence of conservation of angular momentum. Is the consequence of conservation of angular momentum principle. Angular momentum. So here angular momentum is constant. Angular momentum is constant. So here we know that angular momentum L is equal to constant. L is equal to mvr. mvr is equal to constant. That means m is constant, mass of the planet is always constant. So v into r equal to constant. So v is inversely proportional to r. That means v is inversely proportional to r. When we take a planetary motion like this, and let us consider this is nothing but a semi-major axis, and this is nothing but semi-minor axis. Semi-major axis length is nothing but a, and see here we have considered that the sun is at one focus, and the distance from sun is at one focus. Let sun is at this focus, and if the planet is at this location, we call this as perihelion. So at perihelion, this is nothing but, let us consider this is perihelion distance rp. So velocity at perihelion is nothing but vp. So here velocity at perihelion is nothing but vp. We know that the direction of velocity is always tangential to the particle motion. So here when the sun is at this focus, the perihelion distance is rp. That is nothing but the distance from sun to planet is nothing but rp, and the velocity of the planet at a perihelion point is vp. Here vp is, we know that v is inversely proportional to r. That means vp is inversely proportional to rp. As the distance is shorter, as the rp is shortest distance from sun to planet, shortest distance from sun to planet. So therefore the planet has greatest speed at perihelion. Why it is having greatest speed at perihelion? Because the distance is less. If the distance is less, velocity will be more. So the velocity, the planet has greatest speed at perihelion. At aphelion, the distance from sun to this point is nothing but, this is called as we call it as aphelion. The aphelion distance is nothing but RA. So velocity at this point is nothing but VA. We know that VA is inversely proportional to RA. as the distance from sun to planet is greatest here, so the planet speed at aphelion point is less as compared to previous point. Now I am going to discuss about universal law of gravitation. Universal law of gravitation. Universal law of gravitation. Universal law of gravitation states that if two particles are there, let us consider this is mass m1 and another is nothing but mass m2, and center of mass is nothing but here, center of mass of this particle is this one and center of mass of this particle is this one. So now the distance from center to center of the two particles is nothing but, let us consider r. R is the distance. So here the force of attraction between two masses, the force of attraction between two masses is directly proportional to product of the masses and inversely proportional to square of the distance between two masses. The force is directly proportional to product of the masses and inversely proportional to square of the distance. That means a force is directly proportional to product of masses m1, m2 and inversely proportional to square of the distance between two masses. Distance between two masses is nothing but r. Square of the distance is r square. So therefore, by removing proportionality symbol, we will get some constant g m1 m2 by r square. So here g is called as universal gravitational constant. G is called as universal gravitational constant, and its value is given by 6.67 into 10 to the power of minus 11. What are the units? Newton meter square per kg square. Newton meter square per kg square are the units of universal gravitational constant. So here force exerted by m1 on m2 is equal to g m1 m2 by r square. And from Newton's third law of motion, force exerted by m1 on m2 is equal and opposite to force exerted by m2 on m1. That is magnitude of forces are equal. The magnitude of force exerted by m1 on m2 is equal to force exerted by m2 on m1. See here, Newton's, this is law of attraction, universal law of gravitation. We also call it as law of attraction. because here every mass attracts another mass. Every body attracts another body which is at some distance r. So, and the attraction force is stated as, law of attraction force is stated as, the force of attraction between the two masses is directly proportional to product of masses and inversely proportional to square of the distance between two masses. So, if two masses are there, mass m1 and another one is nothing but here mass m2, mass m2 is there. I am connecting the two masses like this, center to center, and the distance is nothing but r. And see here, I am writing force exerted by m1 on m2. Magnitude of force exerted by m1 on m2 is given by g m1 m2 by r square. This is the magnitude, and direction is nothing but, as this is an attractive force, direction of the force is along the line that connects two bodies. See here, when I take a m1 is here and m2 is here. Force exerted by m1 on m2, it is attractive force. So m1 attracts m2 towards it. This is attraction force by m1 on m2. Force exerted by m1 on m2. Force exerted by m1 on m2. Attraction force by m1 on m2. It is along, the direction of force is along the line that connects the two bodies, and the magnitude is given by g m1 m2 by r square. Now force exerted by m2 on m1 is also equal to g m1 m2 by r square. So magnitude is same, but direction of attraction due to m2 on m1 is nothing but, this is the direction. This is the force exerted by m2 on m1. It is along the same line that connects the two bodies, but opposite to force exerted by m1 on m2. This is from Newton's law of motion. So this is force exerted by m2 on m1. So therefore magnitude of force exerted by m1 on m2 is equal to force exerted by m2 on m1. See here, if there are large number of masses are there, so I am taking here m1 and another mass m2 and one more mass here m3, and fourth mass is nothing but I am taking it as m4. Okay, see here, now I am going to find out force exerted by force on m1 by all masses. Find out force on m1 by all masses, because here if we take m1 and m2, there is a force. See here, the line that connects two bodies is nothing but this one. Force exerted by m2 on m1 is nothing but, attractive force exerted by m2 on m1 is nothing but, this is force exerted by 2 on 1. Okay, so and m3 also exerts some amount of force on m1. So force exerted by m3 on m1 is nothing but this one. Attractive force exerted by m3 on m1 along the line that connects the two bodies. This is force exerted by 3 on 1. And one more is nothing but m4 is also there. Force exerted by m4 on m1 is along the line that connects the two bodies like this. So this is nothing but force exerted by 4 on 1. So, how many particles are exerting force on mass m1? m2 is exerting force on mass m1. m3 is also exerting force on mass m1. m4 is also exerting force on mass m1. So, net force is nothing but vector sum of all the forces. Vector sum of all the forces exerted by m2, m3 and m4. All the forces. So net force on m1, F net on m1 is equal to vector sum of f2 on 1 plus vector sum of f3 on 1 plus vector sum of f4 on 1. That means we need to resolve f2 on 1 into components, x component and y component. We also need to resolve f3 on 1 also into components as x and y component. f4 on 1 also to be resolved into components, x component and y component. We can add x component and we also can add y components. So net force is nothing but sum of x components into I cap plus sum of y components into j caps. That means resolve f21 into components, x component and y component, f31 into components, f41 on also into components. Add the x components and y components so that you will get net force in vector notation. I'm going to explain. Sorry. I'm going to explain example number 9.2. Here example number 9.2 is nothing but 3 equal masses of m kg each are fixed at the vertices of an equilateral triangle ABC. Vertices of an equilateral triangle ABC. See here I am writing equilateral triangle. Equilateral triangle here. Right, I am writing equilateral triangle here. Let this is nothing but centroid of the triangle, and all the masses are at vertices of the triangle. M is there like this. And consider that what is the force acting on a mass 2m placed at the centroid of the triangle. This is nothing but centroid, and here the centroid mass is nothing but 2m. Centroid mass is nothing but here how much it is 2m. Okay, so what is the force acting on a mass 2m placed at the centroid of the triangle? What is the force? We need to find out the force acting on centroid mass. So here this mass is at this location, another mass is at this vertex, and another mass is at this vertex. So see, force exerted by this mass m and on this one is nothing but this is the attractive force like this. Okay, so as this is equilateral triangle, this is 60 degrees, this is also 60 degrees, and this is also 60 degrees. Okay, so this off angle will be 30 degrees. Off angle will be 30 degrees. I am writing a horizontal axis like this. So now this angle also will be 30 degrees. This is the direction of force exerted by m on 2m mass. A force is like this and making an angle of 30 degrees. So here the force is like this, F, which is making an angle of 30 degrees with horizontal direction. So when this force is resolved into components, 1 is nothing but we will get, this is the adjacent side, we will get f cos 30, and this one will be f sin 30. F sin 30. So here I am writing this as the f cos 30, and this is nothing but f sin 30. F sin 30. Now I am going to write force exerted by this mass on 2m mass is nothing but force exerted by m on 2m. This is attractive force like this. So this is nothing but F directly along the positive y-axis. Now I am going to consider one more, the last one, force exerted by this mass on 2m is nothing but, this is also a attractive force like this. This is also a attractive force like this. This force is making an angle of 30 degrees with the horizontal direction. 30 degrees with horizontal direction. So along this side we will get f cos 30, and downside we will get f sin 30. F sin 30. See here, f cos 30 is along positive x-axis and this f cos 30 is along negative x-axis. These two cancels each other. So f net is equal to f minus f sin 30, and another f sin 30 is also along negative y-axis, minus f sin 30. Okay, so f net is equal to f minus f sin 30 minus f sin 30 is nothing but minus 2f sin 30. So that is equal to f minus 2f into sin 30 is nothing but 1 by 2. 2 and 2 cancels. So net force equal to f minus f. That is nothing but net force on the particle at the centroid is equal to 0 due to all the masses at vertices of the equilateral triangle. This is the answer for first part. Right. Part B is, what is the force if the mass at the vertex A is doubled? So if mass at the vertex A is doubled, what is the force if the mass at the vertex is doubled, vertex A is doubled? So I am drawing a triangle here, and see here mass is nothing but 2m, and here mass is m, vertex A, B, C. Here also mass is m, and mass at centroid is nothing but 2m. So what is the force now? Calculate the force in this case. Calculate the force in this case if the mass at the vertex is doubled. So here I am going to explain one by one. This is the force exerted by A on 2m. Force exerted by 2m on 2m. So attractive force is nothing but upwards. So F is equal to G m1 m2 by r square. G m1 m2 by r square. Here G m1 is 2m into m2 is also 2m by r square. See here, let us consider this is point O. Here AO is equal to, he mentioned that AO is equal to BO is equal to CO equal to 1 meter. Therefore R equal to 1 here, R equal to 1 meter. Therefore force exerted by 2m at point A on centroid mass is equal to F equal to G into 2m is nothing but 4m square. This is the answer. This is pointing along y-axis. So I am simply indicating with J. J indicates the force is along y-axis. Okay, let us consider this is F1 force. There is no x component, so I am not writing x component here. This F1 is pointing along y-axis, so I have written 4gm square by j. So why I am writing 4gm square? 2 into 2, 4. G is g. M into m is nothing but m square by r square. R equal to 1. 1 square is nothing but 1, simply. Okay. Next, this is F1. And now force exerted by m on 2m. This is nothing but force exerted by m onto m, attractive force. Let this be F2. This F2 is making 30 degrees below the horizontal direction. So F2 magnitude is equal to g. Mass of the first particle is m. Mass of the second particle is 2m. G m into 2m by r square. R square is nothing but 1 square. That is nothing but 2 g. M into m is nothing but m square, 2gm square. And see here, this F2 is resolved. When this is resolved into components, one is along negative x-axis, another is along negative y-axis. So magnitude is this one. So F2 can be written as minus F2x is equal to, see here I am writing F2x now. F2x is equal to F2 cos theta. F2 cos theta. F2 is nothing but 2gm square into cos. Theta is nothing but from positive x-axis to original vector. That is nothing but 180 plus 30, 210. Cos 210. Cos 210 is nothing but 2gm square into cos 180 plus 30. Cos 180 plus theta is nothing but minus cos theta. That is nothing but 2gm square into minus cos 30. So this is the answer. X component of F2. Similarly, F2y is nothing but F2 sin theta. That is nothing but 2gm square into sine 180 plus 30. That is nothing but 2gm square. Sine 180 plus 30 is nothing but minus sine 30. That is minus 2gm square sine 30. So we got x component and y component for F2. So F2 is equal to, we can write it as F2x into I cap plus F2y into j cap. Therefore, F2x is nothing but what? Minus 2gm square into minus 2gm square cos 30 into I cap plus F2y. F2y is nothing but minus 2gm square into sin 30 into j cap. This is nothing but F2. We got F1 already. Similarly, a force exerted by a particle at C on 2m. This is nothing but F3. This is F3. So F3, one component is along positive x-axis, another component is along negative y-axis. So F3 is nothing but G. Mass of this one is nothing but m, and mass at the centroid is 2m by r square. That is nothing but 2gm square is the magnitude. 2gm square is the magnitude. This angle is nothing but 30 degrees, and one is along, this is F3 cos 30, and this is nothing but F3 sin 30. So I can write it as in the component form. That is nothing but F3 can be written as 2gm square into cos 30 into I cap plus y component is along negative y-axis. So minus 2gm square sin 30 into j cap. Okay, this is nothing but F3. So net force on mass which is at centroid is equal to vector sum of F1, F2 and F3. So F net is equal to F1 plus F2 plus F3. What is F1 here? 4gm square into j cap. What is F2 here? Minus 2gm square cos 30 into I cap minus 2 gm square sin 30 into j cap. This is already done. Then F3 is nothing but plus 2 gm square cos 30 into I cap minus 2 gm square sin 30 into j cap. See here, and minus 2 gm square cos 30i plus 2 gm square cos 30i. These two cancels each other. The remaining thing is 4 gm square into j cap. This one I am writing here, and minus 2 gm square minus 2 gm square minus 4 gm square sin 30 into j cap. That is nothing but 4 gm square into j cap minus 4 gm square sin 30 is nothing but 1 by 2 into j cap. 2 to ja 4. 4 minus 2 is nothing but 2. So the final answer is 2 gm square into j cap. That means the net force will be pointing along only positive y-axis. Along positive y-axis, net force direction. This is the direction of net force. So we got the answer as net force on mass which is kept at centroid is nothing but 2 gm square into j cap. Now I am going to discuss two special cases here. The case 1 is case 1. The force of attraction between a hollow spherical shell of uniform density. The force of attraction between, important point, force of attraction between a hollow spherical shell of uniform density and a point mass situated outside is just as if the entire mass of the shell, total mass of the shell, entire mass of the shell is concentrated at the center of the shell. That is nothing but, see here, I am going to explain this in detail. I am drawing a spherical shell like this. And I am drawing a point mass which is kept outside. This is nothing but a point mass of m. This is point mass. Okay, I can imagine this spherical shell is having large number of small masses. I am taking only 3 such small masses which are on the outer edge of the hollow spherical shell. So this is nothing but center C, center of the spherical shell. Okay, so sorry, this is nothing but center C. These 3 I am taking mass m1 and m2, and let this is nothing but m3. So now a force exerted by m2 on m1, force exerted by m2 force exerted by M2 on M. Force exerted by N2 on M. Attractive force is nothing but here the attractive force is, okay, the attractive force exerted by M2 on M. M2 on M is nothing but. So force is being exerted by M2 on M. So attractive force is there. That attractive force is pointing along this direction. So this is force exerted by M2 on M. Okay. And another one, M1 is also there. So now I am taking force exerted by M1 on M. Force exerted by M1 on M is nothing but the direction of force is along the line that connects two masses. So this is the another force. Okay, so this is force exerted by M1 on M. So this force can be resolved into components. X component and this is nothing but Y component. So F1x and this is nothing but F1y. Next, I am taking the third one, force exerted by M3 on M. Force exerted by M3 on M is nothing but this one. So this is force exerted by M3 on M. This is the, when this force is resolved into components, I will get this is F3y. Let us consider this is F3, this is F1 and this is F2. F3y, and in this direction X component we will get in this direction as F3x. So here F1x and F3y equal and opposite, so we can cancel them. So what is the net force? F net. In which direction F net is acting? So y components are absent here. Only F3x is pointing like this. F1x is also pointing like this. And F2 is also pointing like this. So F1x plus F3x plus F2 is pointing itself in the direction of x. So net force is pointing only along x direction like this. So the conclusion is when the masses are distributed uniformly on the hollow spherical shell, the center of mass of all the particles will be located at this point. So the net force due to all the points on hollow spherical shell, net force exerted by all the points on the hollow spherical shell on point mass is considered as the force exerted by mass situated at the center of mass on point mass. This is the conclusion. The force of attraction between a hollow spherical shell of uniform density and a point mass situated outside is just as if the entire mass of the shell is supposed to be concentrated at the center of the shell. Okay, so the net force will be along the line that connects the two bodies, point mass and center of mass of the spherical shell. This is the conclusion. If the point mass is situated outside the cell, And next one, case 2. Here, case 2 is the force of attraction, between hollow spherical shell and a point mass, which is the point mass is situated inside, is equal to 0. See here, I am going to give you the conclusion here. Again, I am taking a hollow spherical shell. Now the point mass is kept inside. point mass is kept inside like this, point mass m, and I am taking three different masses here, m1, and another one is nothing but m2, and one more is nothing but m3. I am taking, we can take large number of masses, but I am considering only three masses here, m1, m2, m3. So here m4 also. Let us take m4 also here. M4. Right? Now, force exerted by m1 on m. Force exerted by m1 on m is like this. Force exerted by m1 on m. Force exerted by m1 on m. Okay. This force can be resolved into components, y component and x component. And next, force exerted by m2 on m. Force exerted by m2 on m is nothing but this is attractive force. This will be pointed like this. Okay. Now, force exerted by m3 on m is nothing but this is the attractive force. This will be pointing along like this. So when this force is resolved into components, we will get a y component like this and x component like this. So here x component like this. And final one is nothing but force exerted by, final one is force exerted by m4 on m. That force is nothing but this one. Okay. So here this force and this force cancels out. This positive x component of force, negative x component of force cancels out. So net force on a particle which is kept inside the spherical shell is always equal to 0. Inside the spherical shell is always equal to 0. This is the second case. Thank you.